Okay, good afternoon to all. So this is our 18th session for the course Fluid Mechanics. First announcement is that on Friday at 5 p.m. we will be having one session on numerical problems, and in this session you can also come up with your doubts if you have any. Okay, and now we will discuss about the Reynolds transport theorem today. Yesterday I have already given the fundamental idea of this theorem, that this theorem helps us in converting our system of equations from system analysis approach to control volume analysis approach. Okay, and system analysis approach is not much feasible for fluid dynamics, so that's why we mainly go with the control volume approach. Okay, so how to do that? For that, what I have done, I have considered over here this red colored outlined. This is nothing but a system, and this particular system I have drawn at some time t. Okay, now if I consider that this system has shifted to this green outlined boundary in some time interval dt, so t plus dt is the new position of the system. Okay, so while this system will be moving in the flow field, of course there will be certain changes in its properties. Okay, so let us consider that B is arbitrary any property of the system. So what is B? B is nothing but any property of the system. Fine. And what will be its intensive form? So we know that if B is any extensive property, then its corresponding intensive form I can specify as beta, which is nothing but equal to B by M, where M is mass of the system. Okay, so beta is nothing but my intensive form of property B. Is this point clear? Now, if for this system I have to determine that how much change is in the property B, then how I can determine? I can simply say that d by dt of B for the system. Okay, so this is something which we already know. Okay, but what we have to do now, we have to represent this in terms of the control volume analysis. Okay, so what I can do, I can consider that through this, if you see, if this is my control volume, so whatever this red colored outline, this was the system at time t, and green colored outline is system at time t plus dt. If I consider that my red colored outline is nothing but also the control volume, this is also a control volume. Okay, so if this is a control volume, then what I can say? I can say that from this side, particularly this hatched portion over here, this hatched portion is nothing but some amount which has entered, and this hatched portion over here some amount which has actually gone out of the control volume. Is this point clear? What I am trying to say? So this red colored thing is nothing but a system. Now green colored thing is new position of the system. But what I am trying to say over here is that this dashed black line, which is nothing but completely following the red colored line, it means that it is nothing but the boundary of a control volume which is fixed in space, because control volume at the moment I am considering it is not moved. Okay, so if this is a fixed control volume in space, then I can say that from this left portion, because these inward arrows are showing that some portion has entered into the control volume, and this portion over here is showing which is the portion which has gone out of the control volume in time period dt. Okay, is this point clear? So now the total change in property of the system will be equal to, first it will be having two components. How it will be changing? First is rate of change of property within the control volume. What will be rate of change of property within the control volume? Okay, So I can assume that beta is my intensive property, okay, and if dV is my any elemental volume, if dV is any elemental volume over here, so if any elemental volume is dV, and let's consider that corresponding to this elemental volume dV, my value of property was beta, okay. So what I will be finding that if this dV is elemental volume, then mass is nothing but rho into dV. Rho into dV is the mass, okay. And for this element, how much will be the property? Property will be nothing but beta times mass. So beta times mass into beta times rho dV. Is this point clear? Anyone is having any doubt? So what I have done, because I have a finite sized control volume, okay. In a finite sized control volume, at different locations of the control volume, there can be different values of property. So I am considering that if I have infinitely small sized control volume dV, and that particular control volume is having density rho, then mass of that small fluid element will be rho into dV, okay. And if beta is intensive property, then value of total property for that small elemental volume will be nothing but beta times rho, okay. Can you tell me what will be the total value of the property? Total value of the property will be nothing but integral of beta rho dV, okay. So if I do the integration of this, that will be telling me the total amount of property, and this integral I am doing nothing but over the volume. So that's why I should write it as V in the limits of integration, okay. Now I am talking about that rate of change of property. So rate of change of property within the control volume I can write in the form of d by dt of integral over the volume beta rho dV. Is this point clear? Okay. So if within the volume of the control volume any change is happening with time, that I have actually quantified over here. Okay. Now second thing, how I can quantify, second thing is changes in property across control surface of control volume. So what do we mean by control surface? The boundary of the control volume is nothing but called as a control surface, okay. So through the boundary also something can enter in and something can go out, okay. So if I have to account that portion, so this is nothing but simple case of a, say, water tank. So in the water tank you have one inlet line, one outlet line, okay. So if from inlet line water is entering and from outlet line water is going out, then what will be the net change in water height or water mass within the tank? That will be nothing but through the boundary, whatever the net effect of output minus input is there, okay. So same way now we have to define over here that how much change in property is happening through the boundary of the control volume. Is this point clear? So you can see that particularly this portion of the boundary is something which is allowing some fresh thing to enter into the control volume, and this portion of the control volume, this particular boundary of the control volume is something through which my fluid is going out of the control volume, okay. So I have to quantify out portion minus in portion, that will be my net change across the boundary of the control surface, okay. So how to quantify that? To quantify that, let's consider that I have small element over here over this control surface whose area is dA, okay, and its outward normal vector is n cap, okay, and say v vector is my value of velocity vector at this control surface, and the angle between this unit normal vector and v vector is nothing but theta vector, okay. So if this is the situation, can you tell me how much amount of property is going out of the system? So amount of property going out of this small elemental area dA, how we can quantify? First we have to quantify the volumetric flow rate. at which fluid is going out. So volumetric flow rate is nothing but area into velocity. Okay, but when we do area into velocity, we have to always consider our component of the velocity normal to the area. So I can write V vector dot n cap times dA. This is the volumetric flow rate. If I have to find out the mass flow rate of the fluid, then I will be multiplying this with density rho. Fine. Is this point clear? Then I will be multiplying it with density rho, and or in simple sense I can write, let me not first use the vector notation. I can just write V dot n cap as nothing but V cos theta. Okay, because in between V vector and n cap I have angle theta, so I can write V cos theta as the component of the velocity which is in the direction of outward normal. So rho V cos theta into dk. So this is the, and this dA, whenever I am considering, this dA portion is nothing but the portion of the control surface which is leading the velocity going out of the surface. Okay, now this is the total mass which is going out through this area dA. When this mass is going out, from the thermodynamics we know that mass also carries certain amount of property with it. Okay, so say beta is the property it is carrying with it. Fine, all are fine with this what I have written over here. So basically first I have quantified the rate, mass flow rate which is going out, and then I have multiplied it with the property beta. Okay, so I can say that the change in property across the control surface will be actually outflux of property minus inflow of property. Fine, how much is going out minus inflow. So outflow is, for elemental area outflow, just now I have shown you that it is nothing but beta rho V cos theta times dA out. Okay, and if I have to find it for the finite sized area through which it is going out, then I have to take integration of this for the control surface. Fine, all are fine with this. Similarly, there will be some amount which is actually entering into the control volume through control surface. So here you can see this portion of the control surface is showing where amount is entering. So what I can do, I can take a small elemental surface area dA over here. Let me assume now outward normal vector is like this. This is n cap, and let me consider that this is my velocity vector which is now inward. Okay, and once again angle between these two is say theta. Fine, so how much will be the now inflow? In this V and N, now we are having opposite directions, so we will be having negative. Okay, so that is the reason I will be writing it as minus integral over control surface beta rho V cos theta, and when I am doing this dA, I am doing this integration for the control surface, only I am considering the portion which is having velocity inward facing. Is this point clear, or anyone is having any doubt in this point? Okay, so what we have quantified now, I have quantified that within the control volume the change will be because of two things. One is if any change is happening within the volume, and second change I have quantified which is taking place across the boundaries of the control volume. Okay, which is called as control surface. Okay, so now I can say that the total change in property of the system d by dt of V system is nothing but equal to d by dt of control volume beta rho dV. Please make this clear correction. This V is actually velocity, and when I am using this V, then it is volume. So let me use V bar for the volume, otherwise it may create confusion. So V bar I am using volume. Okay, is this point clear? Then this is change within the control volume, then I will be having actually change across the boundary of the control surface. So that change is actually this one. So this change is how much? Beta rho v cos theta into dA out integration over control surface minus beta rho v cos theta into dA in. Is this point clear? Okay. So now I am able to relate the change in system property with changes in the control volume. My left hand side nothing but represents the changes in property of the system. On the other hand, right hand side represents the changes of the properties within the control volume. Okay.
Why will not given the rate at which the property is changing across the controls?
This is in the rate form only, because if you see rho v cos theta into dA, this is mass flow rate. So mass flow rate multiplied by property is in the rate form of the property. Okay. Is this one clear? So this particular theorem is called as nothing but Reynolds transport theorem. But while we have considered this theorem, one simple assumption we have made is that our control volume is fixed. Control volume is actually not moving. If we have a moving control volume, then actually situation will be different, because fluid will be striking with the boundaries of the control surface then at relative velocity, not at the absolute velocity. Is this point clear? Okay. Now the theorem which I have written over here, so you can see this particular term over here is called as actually flux term, flux of the property. Okay, flux of the property means the net change in the property across the control surface, across the area. So that's why we call this as nothing but flux of the property. Okay. Now in a simple sense, as I already told you, if I simply consider this flux term, I can write it as Cs beta rho v cos theta into dA out minus integral control surface beta rho v cos theta into dA in. Now from our simple understanding we know that v cos theta is nothing but component of velocity normal to the area and dA is area. So this will be becoming volumetric flow rate, and if I multiply with density also, this will be becoming total term as nothing but total mass flow rate which is going out. Okay, and this will be becoming total mass flow rate which is coming in. Okay, so that's why this flux term I can simply also write through the control surface as beta times dm dot out minus integral over the control surface beta times dm dot in. Point is clear? Now one more simplified version of this equation also I can write if I use the vector notation. Okay, so if I use vector notation for the flux term, then how I can write it? I can write flux term in vector notation as nothing but integral over the control surface beta times rho, and in place of v cos theta, if I write it as v vector dot n cap vector and then dA. What will be v vector dot n cap vector? It will be nothing but v cos theta only. Okay, it will be v cos theta only, but it will be v cos theta when v dot and n cap are oriented in the same direction. Okay, when these are oriented in the opposite direction, then it will be minus v cos theta. So it means that if I write this control surface, this flux term by using integral over the entire control surface and simply use v dot n cap, then depending upon the portion of the control surface, it will be accounting for both inflow as well as the outflow terms, because this is nothing but a vector term. Okay, is this point clear? This vector term will be positive for outflow and it will be negative for in. Point is clear? So because of this, I can simply write this equation also in the uh, generic form and with little bit compact notation as d by dt of integral beta rho dv bar over control volume plus integration over the control surface rho beta v vector dot n cap times dA. So this is another. Now because our control volume is fixed in space, so if control volume is fixed in space, then I can take this d by dt even within the integral also. So I can first do d by dt and then use integral. So even I can write it in the alternate form as, particularly this first term of right hand side, as I can also write it as integral over the control volume del by del t of beta rho dv bar. Okay, because this is nothing but fixed in space. But if it is not fixed in space, if it is moving, then also for a rigid motion of the control volume, still I can put this time term inside. But if my boundary of the control volume is deformable, so then volume is actually also changing with time, then I cannot put this time derivative inside. In that case, first I have to do the volume integral and then its derivative, the time. Okay, is this point clear? Point is clear what I am trying to say over here. So if my control volume is of fixed size, its boundary is not deforming, then of course its volume will remain the same. So whether first I do time derivative or first I do volume integral, it will not make any difference. But on contrary, if it is deformable, it is changing its size, then in that case, first we have to do the volume integration, then only we can take the time derivative. Okay, so now let's consider the second case. So this first case was when our control volume is actually fixed in space. Okay, now second situation can be if my control volume is moving with constant velocity. Constant velocity. So say this control surface is having some velocity v vector s. Okay. So if your finite sized control volume is moving with the constant velocity, then what will be happening? Over here we have to consider that the frame of reference in which we are considering the fluid motion, say if I say v vector is nothing but velocity of fluid. So the frame of reference with reference to which I am finding this fluid velocity, if I have the same frame of reference, okay, which is giving me Vs as the velocity of the control surface, then I can simply define the relative velocity as nothing but V vector minus Vs vector, with which boundary of the control surface will face the velocity. Is this point clear? Point is clear what I am trying to say. Say if V is velocity of the fluid, okay, and Vs is velocity of the control surface, and both are with reference to the same frame of reference. In that case, any boundary will experience the flow of fluid with nothing but relative velocity, which is the vector subtraction of the fluid velocity and the control surface velocity. Point is clear? If you are standing over here, if some fan is blowing air on you, then you will be experiencing V velocity. You are standing over here. If you are moving towards the fan with Vs velocity, then the rate at which fluid will be approaching you, that will be nothing but V minus Vs. Okay, so that is what I am trying to say. Okay, so if V relative is the velocity at which fluid is being experienced by the control surface, then what I will be doing, my Reynolds transport theorem will be becoming dV system by dt equal to d by dt of integral over the control volume beta rho dV bar plus what I will be getting? Tell me. Integral over the control surface beta rho and what I will be having now? Earlier I was having v vector dot n cap. Now it will be V relative vector dot n cap times d. Point is clear? This point is clear? Okay. Now let's consider that third case. CV is moving with what type of velocity? CV is moving with variable velocity. So what I am saying once again, that my control volume is of fixed shape. Its shape is not deforming, but it is now moving with variable velocity. Okay. So if it is moving with variable velocity, then what will be the velocity of control surface? So velocity of control surface will be V vector S, but it will be function of time. Okay, it will be function of time, because with time it is varying. Okay, whole control surface means each and every point of the control surface is moving with velocity Vs only, because it is a rigid control surface, but what is happening, its value is changing with time. Okay, so if this Vs is function of time, then can you tell me now, relative velocity, will it be only function of time, or will it be function of space and time? This V vector, what will be the velocity of the fluid now? So now if you define the relative velocity, that will be nothing but V vector as function of position vector as well as the time minus Vs, which is only a function of time. Point is clear? See, V is velocity of the field variable, velocity of the fluid flow. So velocity of the fluid flow can be different at different positions. So that's why velocity of fluid flow will be having functional dependence of both position vector as well as the time vector. But velocity of surface, because surface is a rigid surface, okay, so that's why its velocity will be only function of time. Okay, and all the positions across the control surface, these will be moving at the same rate. Okay, so now difference is, only thing we have to substitute this formulation of VR over here, except that whole equation remains the same. Okay, but estimation of VR will be more complicated. Fine. Then final situation. What will be final situation? Control volume is, this is the most generic one. Control volume is deformable as well as having variable velocity. Of course, if it is deformable, it will be having variable velocity. It need not to be specified. Okay. So in this situation now, this Vs will also depend upon the position of the control surface, because different portions of the control surface can deform with different values. Okay. So ultimately my relative velocity in this case will become V vector position vector comma time minus, this is surface velocity, this is also a function of both position vector as well as the time. So analysis become more complicated. This point is clear? So in this case analysis will be becoming more complicated. Okay. Anyone is having any doubt up to this point? Okay, now say if I have a case where control surface has finite number of inlets and outlets. If a control surface has finite number of inlets and outlets, then what will be happening? So the meaning is, say this is my control surface, but through all the portions of the control surface flow is not happening. Say all these blue colored portions which I have shown, these represents as the outflow. Okay, and Similarly, this black colored portions, this represents the inflow. So I have now multiple inlets and outlets over the control surface. Only in these portions we are having velocity. Other than that, whatever the portion of the control surface is there, here velocity vector is equal to 0. Okay, so it means I have finite number of inlets and outlets on the surface. Okay, so if I have finite number of inlets and outlets on the surface, then what will be happening? Can you tell me? Now my dB system by dt will be d by dt of changes within the control volume. So changes within the control volume are beta rho dV vector. Okay, sorry, not vector, dV bar volume. Now I was having integration. Okay, so in place of the integration I can use summation now. So plus summation of beta rho V I, say I is my, what is I? I is my index for number of, yes, I am talking about ith, say outlet over here. And here I will be considering A out, means area of that ith outlet. So A out I. Fine. Minus summation of beta rho V I into A in I. So this is the portion for outflowing outlets and this is the portion for inflowing outlets. Sorry, I must use over here dA only at the moment. dA out I and dA in I. Fine. Okay. Now if I have to once again write it in the compact form, then this whole I can replace with, how I can replace? This entire term I can write summation beta rho V vector dot n cap I times dA. So this will be taking care of the plus and minus. Okay, V vector dot. Now if I have one dimensional inlet, if I have 1D inlets and outlets, what is the meaning of 1D inlets and outlets? We do in thermodynamics. What is the meaning of 1D inlets and outlets? Sorry, I will be putting over here dA and integration. Yeah, integration also I will put, because right now I have not considered the 1D inlet and 1D outlet. So what is the meaning between 1D and this dA? That I am trying to say. So the meaning is, if say this is my inlet, at this inlet, at this point there can be different velocity, at this point there can be different velocity, at this point there can be different velocity. Okay, so I am considering the integral of velocity for all the entire portion. So that is why I have written this integration also. Okay, so this integration now does not mean for the entire control surface. This integration is only for the ith inlet or outlet which we are referring to. Okay, because in that particular complete area also there can be variation of velocity. So that is the more generic case. But now I am taking the next assumption as 1D inlet and outlet. Now this dA integration will cancel and it will become A. Okay. Have you understood this point? So now what is the meaning of 1D inlet and outlet? We do all our thermodynamic analysis is assuming 1D inlets and outlets. You might have studied steady flow energy equation. What we are considering? At any ith inlet, we are saying velocity is Vi, and that is nothing but average velocity at each and every portion of the area. Fine. When I am considering this particular formulation which I have specified over here, as per this formulation, if this is my inlet, at this inlet I can have any random variation of velocity. For example, some parabolic type of velocity variation. Okay. When I am referring to the 1D inlet and outlet, the meaning is that over the entire area, I will be having same value of velocity. Okay. Here what I am trying to say that I have the same value of velocity at different portions of this inlet. Point is clear? The meaning of one-dimensional assumption is clear? So 1D assumption tells that at different portions of any inlet or outlet, there will be same value of the property for a particular inlet and outlet. Okay, so it means some single value is defined for the complete inlet and outlet. So when single value is defined, then I can get rid of this blue colored integral sign from inside, and I can simply write this term as nothing but, how I can write? Let me write the complete equation. Have I deleted it? Okay, let me open the new page. Oh, it is there. Okay, so now what I will be doing, d by dt of B system equal to d by dt of control volume beta rho dv bar plus what I will be getting. Now this velocity, what I was connecting to small elemental area dA, instead of connecting this to small elemental area, I can connect it to the total area of the inlet, because for total area of inlet it is a single value. Okay, so that's why I can write now only simple summation without integration, beta rho v into A, this for ith point at outlet minus beta rho v A for ith point at inlet. Point is clear? Now, what is this rho v A? Rho into area into velocity is nothing but mass flow rate. Okay, so I can simply write this as d by dt of integral control volume beta rho dv bar plus summation of m dot out I into beta I minus summation of m dot in I into beta I. Okay, point is clear? Earlier, what was happening when the case was not one dimensional, I cannot write V value for total area. So V value was only for elemental area. That's why I was putting integration also along with the summation sign. Okay. So integral was over the particular inlet and outlet, and summation was to include all the inlets and outlets. Okay. Now, because over the entire area, velocity, beta, density, all the properties are having unique value, so that's why I am just writing it as a total. Fine. Integration is not needed. All are clear up to this point? Now the benefit of this Reynolds transport theorem is that if you have understood it thoroughly, you can apply to arbitrarily to any property and you can get all the form of governing equations for the fluid flow for a control valve. Okay, because B I have nothing but taken arbitrary any property. Okay, so let me show the application of Reynolds transport theorem for conservation of mass equation. Okay, so if I talk about mass, then B is nothing but equal to M. Okay, mass is my property. What will be beta? Intensive property per unit mass. So beta will be equal to 1 over here. apply now the Reynolds transport theorem for a fixed control volume. So majorly we will be deriving all the equations for fixed control volume, because that is what in majority of the cases of this course will be there. For some cases we will be having the moving control volume. These we will be referring to case by case cases. Okay. So for fixed control volume, what I will be getting now? dm system by dt equal to integral over the control volume del by del t of beta. Beta is 1 rho dv bar, okay, plus, tell me, integral over control surface. Beta is 1 rho v cos theta into dA out minus rho v cos theta into dA in. What is clear? Now we know that if I have a system of fixed mass, because no mass is entering into the system, no mass is leaving the system, so mass of the system will remain constant. So dm system by dt must be equal to 0. Fine. So ultimately I will be getting nothing but my continuity equation as in integral form as del by del t of rho dv bar plus, let me write it in the vector notation now. So rho times v vector dot n cap into dA over the control surface is equal to 0. So this is nothing but continuity equation for a finite sized control volume. Okay, because I am writing it in the integral form. This is conservation of mass principle. Okay, so earlier dm system by dt equal to 0. This was conservation of mass principle for a system. Now with the help of Reynolds transport theorem, I can apply conservation of mass principle for a control volume. Clear? Point is clear? Now if I have once again finite inlets and outlets, what will be happening? Del by del t of rho dv bar over the control volume plus I will be having now summation. If I have finite number of inlets and outlets, then in place of integral I can take summation sign, okay, and of course my velocity at each inlet and outlet is not one dimensional, so that's why I have to use integration, but this integration is only for a fixed inlet and outlet. So integration over I, okay, AI, I can write AI, area I, and so limit of integration is AI, and this will be becoming rho v vector dot n cap into dA, and this dA also I. Fine. Point is clear. This must be equal to 0. So this is for finite sized inlets and finite number of inlets and outlets. Okay. Now if I have to do this thing for one dimensional system, then what I will be getting? For 1D system, integration will further go away plus summation rho v vector dot n cap into AI equal to 0. Okay, because over the entire area of the inlet I have a fixed value of the velocity and density. Okay, this point clear? Now let me introduce the next assumption. If flow is incompressible, what if flow is incompressible? Density is equal to constant. Okay, so for incompressible flows, density will be constant. Now density is constant, dV is constant, total volume, because we have considered a fixed control volume. Okay, So integral rho d by dt, this term will be becoming equal to 0. Point is clear? Okay, so first term will be becoming equal to 0 for a fixed control volume. How I can prove this? Because I can write it as nothing but d by dt of control volume rho dv bar. Now this control volume size is fixed. So this integration will give me a unique value of mass, and dm by dt will be becoming equal to 0. So this will be 0. Then for incompressible one, I have got summation of rho v vector dot n cap into ai equal to 0. Now I have considered all inlets as well as outlets. If I segregate inlets and outlet, then what I will be getting? Summation for all outlets rho v vector dot n cap ai will be equal to summation for all inlets rho v vector dot n cap into ai. Okay, is this point clear? Because this is nothing but outlet minus inlet equal to 0, so outlet will be equal to inlet. So if you have a fixed size control volume, density of the fluid is assumed constant, so any change within the control volume will be only because of inlets and outlets. Okay, there will not be any other change within the control volume. Okay, so from this, now density is constant, I can take rho out. Rho will be cancelling out, and ultimately I will be getting summation out for v vector dot n cap ai, summation in for v vector dot n cap ai, and ultimately this area into velocity, what it is? If I write it, summation of out v cos theta into ai equal to summation in v cos theta into ai, then ultimately what is v cos theta into a? Volumetric flow rate. Okay, so summation of q I equal to summation of qi for all inlets. Is this one clear? Point is clear? Now, if I have to define the flow rate through any inlet, say I have arbitrary any inlet over here, this is my inlet, and over this inlet my velocity is actually varying. Velocity is not fixed, but it is varying. Okay, so how I can determine volumetric flow rate for this inlet? Volumetric flow rate for this inlet will be nothing but equal to integral of v cos theta into dA. Okay, and this volumetric flow rate I can also determine by just writing it as, if I know that for this some hypothetical average velocity is v average, so v average into area. This is how also I can write the volumetric flow rate. If I know any hypothetical average velocity at this inlet is nothing but v average. Okay, so from here I can simply say that my v average will be nothing but 1 by area integral of v cos theta into dA. This is area integral over if I consider the area of this entire inlet is nothing but fine. How I can estimate the average value of the velocity at a particular inlet? Okay, so if it is given to you in the question that velocity of this inlet varies with time, varies with the how it varies with different positions, then you can put it into the integration of area and you can estimate the average value of the velocity. Fine. Anyone is having any doubt? Now same thing, if I want to apply for Newton's second law of motion. What is Newton's second law of motion? This is nothing but related to linear momentum. So rate of change of linear momentum is equal to force. Okay, now here linear momentum is my property, so B is nothing but m into v. What will be beta? Beta over here will be velocity vector. Okay, so beta is velocity vector. Can you apply now Reynolds transport theorem? So I can say that d by dt of m into v vector for system will be equal to integral over the control volume. Beta means v vector times rho dv bar del by del t plus what I will be getting? Integral over the control surface. What is beta? V vector rho into v vector dot n cap dA. And what is rate of change of linear momentum of the system? This is nothing but equal to net force acting on the system. So this will be equal to F vector. Fine. So force acting on the fluid element, I can simply calculate net force acting on the fluid element. I can simply calculate by just writing Reynolds transport theorem for property linear. Is it clear to all? Anyone is having any doubt? Okay, so we will try to see the implications of this particular equation in our next lecture. How we can use this for solving the numerical problems and then determining forces acting on the fluid. Okay.